Over the last few years, we built a specialized hardware and software stack to support the training and inference of large language models, or LLMs. Our AI supercomputer in Azure can train models that are hundreds of billions of parameters in size. The original GPT-3 was 175 billion parameters, but we built larger models than that since. For example, Microsoft's Megatron Turing natural language model has 530 billion parameters. And as newer generations of LLMs are released, they're going to be even larger. The thing we had to support with LLMs like GPT is their self-supervised learning, where they learn about a language by examining billions of pages of information over and over again. That directed how we approached building a specialized hardware and software stack that can support the efficient running of models of that massive scale. An efficient infrastructure for running things at that size is really critical. You have to deal with failures that are happening on a regular basis. Every few days, and even sometimes more frequently when you're at a large scale, something's going to fail, like a server's going to fail or a network link's going to start to flap. So you've got to be able to minimize the rate of failures. When one happens, you got to be able to diagnose it very quickly, and then you got to be able to fix it very quickly. A lot of things had to come together to build a hardware and software stack that could support that kind of scale. We've invested a lot in our data center infrastructure with state-of-the-art hardware that we run in Azure globally for raw compute horsepower. One of the key things we do is cluster GPUs with a high bandwidth network to provide connectivity required to efficiently train them. We layer on top of that Azure software platform optimizations, where we have, for example, enlightened the platform and the hypervisor to be able to access those network GPUs so that the performance is comparable to running on bare metal, but with a full manageability layer on top. As we move up the stack, we've also developed and integrated open source frameworks like Onyx for model portability, and the DeepSpeed framework that came out of Microsoft research that helps componentize these models so that they can train across interconnected GPUs at greater scale and speed. We collaborated with NVIDIA to deliver purpose-built AI infrastructure with NVIDIA GPUs. The multiple GPUs required to train LLMs don't all operate on the same board or even the same rack. They're spread out due to the power consumption and heat. And we want to network and cluster as many GPUs as we can. And the new H100 VM series in Azure, powered by NVIDIA H100 Tensor Core GPUs, lets you choose one or more GPUs, cluster up to 8 GPUs per VM using NVLink, and scale out to thousands if your demands grow using NVIDIA Quantum 2 InfiniBand networking. So from a throughput perspective, starting with a single node using NVSwitch and NVLink 4.0, bisectional bandwidth can reach 3.6 terabytes per second between 8 local GPUs. And to put that in perspective, at that speed, you could download about 80 4K videos in less than a second. Project Forge introduces transparent checkpointing, where it periodically saves the state of a model incrementally without the model's code needing to do anything. That way, if anything fails, it can quickly resume for the most recent checkpoint. We combine this with our integrated global scheduler that pools GPU capacity from regions around the world. So if you need to pause a job to prioritize another one, that allows us to migrate that pause job to another region if necessary and available, with minimal impact on its progress. But if you want to focus on building and running models, you can take advantage of our frameworks and MLOps services. So for example, you can use our Onyx runtime that I mentioned, or use our DeepSpeed training framework for more efficient distributed training. And you can use Azure Machine Learning's PaaS services that natively integrates with our AI infrastructure to build your models. And with AML, you can easily fine-tune models like GPT-4 and to deploy the fine-tuned models as managed services for your own applications to use. Well, there are a lot of really interesting use cases where customers are using training and inference on top of our large-scale infrastructure. One of them that's one of my favorites is Wave. It's a company in the UK that is a leader in autonomous driving technologies. So what they're doing is specializing in distributed AI-powered autonomous systems for self-driving vehicles using primarily vision-based machine learning. And they're using our AI supercomputer to gather, manage, and train those models on millions of hours of driving data per year. That's petabytes of data consisting of images, GPS data, and data from other sensors. Each individual training sample can be hundreds of megabytes in size. And by comparison, a training sample for a LLM is typically just a few K in size. So they're also training models with billions of parameters and use Azure Machine Learning and AKS for large-scale distributed deep learning and orchestration. And that's key because Wave requires a lot of linear scaling, optimal memory utilization, and a fast GPU interconnect with minimal latency with high throughput. And that's where we excel. And then finally, for the consumers of those models, like people that are using Azure OpenAI, when they send their queries in, that data is also very sensitive. So with confidential computing, You can protect all of that data end-to-end in a trusted execution environment, which is provided by hardware with a hardware root of trust that only you have access to. That means the data in memory is protected and encrypted. Data is only in the clear while running inside of that TE, and it's re-encrypted and unreadable when it leaves that TE. That prevents third parties and processes, including Azure operators, from accessing the data and models. That enables confidential multi-party collaborations and what we call confidential data clean rooms, where parties can combine their data sets for training, and each party is unable to access anyone else's data. Everything we do to build these systems pays dividends to anybody using Azure, whether you're using AI or not. It means they're going to have lower cost, higher scale, more efficient data centers, more powerful software frameworks. Right now in the area of AI, we're in the process of rolling out those NVIDIA H100 GPUs for AI and HPC. And you're going to see us make Project Forge available for everyone to use as you train and run your AI models, like I mentioned earlier.